Welcome back everyone to George James & Associates Research Tools channel. Today I'm going to very briefly walk you through what we should do with continuous variables. So they're not dichotomous, which my past videos in this mini-series has covered, and they are not categorical, which is the last video that I posted on race and ethnicity. So that took a lot of work. Categorical easily takes the most work. Continuous is very easy. So what do you do with continuous variables? So let's say here we have, how many children do you have? You don't even need to rearrange anything. You don't need to do any of that stuff. So you can go back here to ID. You notice that these are in alphabetical order. And so then the data is in its original form. So what we're going to do is we're just going to say children, and we know that that's continuous. So what we're going to do then, actually, I guess I should name it after I copy everything over. How many children do you have? Copy that, paste it there, rename this column to children. That's it. 1 minute long video. No, why? So why do you just need to cut and paste it over? And why does it matter if the vast majority of the students have no children, which is the case here? Because it's continuous. And especially in ordinary least squares regression, where the dependent variable is also continuous, the only thing you have to make sure of with continuous variables is that the range is in the ballpark of your other continuous variables, which children is going to be. Income, however, is not going to be, right? Income is not, because here, imagine this, right? You have a computer program and it's sitting here saying, okay, number of children, 0, 1, 4, 7 is the highest I saw, but most of the time it's 0, somewhere between 0 and 4. Okay, that's easy. That's easy numbers, right? So you just imagine 0 to 4. But then you go over here to income, where income is like 20,000, 19,000. What are some other values that we have? 40,000, 90,000. So how do you compare when you're trying to shove these two variables in the same model? How is the computer going to handle numbers like 65,000 with one variable and 2 with another variable, right? So the problem with that then is that when we're going to do that, what we're going to do is we are going to come over here and we are going to create another variable for income. And actually it's going to be log income. And what we're going to do is we're going to just take the natural log of all these numbers. And that's going to fit. It's going to take all the way up to like 90,000 or something. And it's going to condense it down to numbers between 0 and, I don't know, off the top of my head, I don't know what the log is in 90,000, but it's I guess I could do it on the calculator. Let's see, can I do it on the calculator? Those of you who are math whizzes probably already did it, but let's see. Can I do the scientific calculator? Yeah, so if I do, 90,000, that's how you do it, I think, right? And log. Yeah, so it's 4.95. That's a much easier number to deal with in your regression model than 90,000. Right, so the log is going to take, all the log is doing here is it's flattening the number, it's squishing the numbers together when the range of the numbers are so vast. That's all log does, right? It's logarithmic. Like earthquakes. You could measure earthquake in terms of dollars of damages. You could measure earthquakes in terms of pounds per square inch. You can measure it in terms of millimeters, but that's really like millimeters is in terms of the shifting, the amount of shifting of the tectonic plates under the earth, under the surface of the earth. But we don't think, it's hard to put that on a scale, right? We need a frame of reference. And the frame of reference is, in this case, when we're trying to compare things numerically, the frame of reference is from what to what? Right, from X to Y. And X to Y needs to be a manageable number. We can do that with income, but again, it's not just looking at income, it's looking at income and comparing the average distance, right? The standard errors, the average distance between the mean and particular observations. And we're doing that across multiple variables at the same time. That's what the regression software does. And so to make it easier, we need to compress, we need to flatten all these massive ranges like income, net worth, things like that. And you need to flatten it. So that's why it's important for continuous variables to, if you have something like income, take the log of it, right? So in this case, because the dependent variable is going to be number of hours worked, right? So the number of hours worked is going to be like no higher than 100 probably. So that's fine. I think that's still, that's fine. I mean, we could take the square root of that if we wanted to, but we're probably just going to leave it as is in just the number of hours worked. Actually, I'm sorry, that's not the dependent variable. The dependent variable is the grade. It's the numeric grade. That's our dependent variable. So between 0 and 100. So it still is continuous, but there are only what, 101 possibilities if you include 0. And so that's the dependent variable. We're going to leave it as it is, right? So that is that is just the normal value of the final grade. But then when we come to things like income, we're going to take the log of that. So it's going to be a linear log model, dependent variable, independent variables. If at least one of the independent variables, right, is we've taken the log of it, then it becomes a logarithmic model, because there's at least one variable in there that is logarithmic, right? Or that we've flattened somehow. I would say it's logarithmic. It's a linear log model, even if instead of taking the log, you take the square root, or you divide it by 100, whatever it is that you do, right? But any time you're reading through something and you read that you're reading a research article or something, and they said that we utilize a linear model, that just means that it's OLS, and that means that the dependent variable and all the independent variables are in their original numeric state. So there was no transforming of any variables. If you're reading further and they say, oh, and in this model, this was a log linear model. So what that means is that the dependent variable was transformed, but none of the independent variables were transformed. So we have what? Linear, linear, and then linear log. Linear log is the dependent variable is in its normal state, not transformed, but at least one of the independent variables was transformed. So those are the differences, right? Log, linear, log, linear. Only four options there. So that's less important, but again, if you're confused whenever you're reading through journal articles and they said, "Oh, we used a linear log model," that's what they mean. So just figured I would throw that in there for some additional information. Whenever we get to in our data set, when we get to the point where we're looking at the income, then I will take the log of it. I don't think I'm going to do that right now because there are other variables before then. I like to keep them in the order. So yeah, we just did number of children. That was very simple because we don't need to transform it. We literally just copied and pasted it over because it's a continuous variable, and then I just rename the column. That's it. That's all you have to do. So very, very simple. And that's it for this video. Thank you so much for watching, and we'll see you next time.